In last video, we have seen about moving coil galvanometer, its construction and working. Then we have seen what is magnetic dipole moment, also magnetic potential energy of magnetic dipole. Then Biot-Savart law. In this video, we are going to see here some applications of Biot-Savart law. The first application of Biot-Savart law is to find the magnetic field produced by current carrying straight wire, long straight wire. After that, we will find the force of attraction between the two parallel wires carrying current in same direction. Force of attraction between two parallel wires carrying current in same direction. And then, second application of Biot-Savart law, to find the magnetic field produced by circular wire carrying current. First, I will explain here magnetic field. Magnetic field due to long straight wire. Of course, current carrying straight wire. Magnetic field due to long current carrying straight wire. Take one wire which is infinitely long. This is the wire which is infinite to both sides. Consider that through this wire current is passing in this direction. Current is passing through this wire in this direction. This wire through which current passes produces magnetic field around it. Produces magnetic field around it. The magnetic lines of this magnetic field we can obtain with the help of right hand thumb rule. What is this right hand thumb rule? Hold that wire in right hand such that the thumb will come in the direction of current. Then this cold finger gives us the magnetic lines of force of that magnetic field produced by that wire. You get magnetic lines of force here circular. Remember that magnetic lines of force produced by straight wire come circular. The tangent drawn to these magnetic lines of force at some point will represent the direction of magnetic field at that point. Tangent drawn to these magnetic lines of force at some point will represent the direction of magnetic field at that point. Here, we are going to find magnetic field produced by this current carrying straight wire at point P. Suppose this is that point P. The distance of this point P, take perpendicular distance equal to R. Suppose this OP is the perpendicular to this wire. OP is the perpendicular to this wire. Length OP we have taken equal to R. the perpendicular distance of the point from the wire is equal to r. This point O, which is foot of the perpendicular, this point O, which is the foot of perpendicular, we will consider here as the midpoint of this infinitely long wire. We will consider here as the midpoint of this infinitely long wire. The meaning is that half wire is present above this point O and half wire is present below this point O. Half wire is present above point O and half wire is present below point O. For upper part, we can consider limits for length 0 to infinity, while for lower part also, we can consider limits for length 0 to infinity, considering point O as the origin, starting point, reference point. The limits for length for upper part will come 0 to infinity, and for lower part also comes 0 to infinity. Now, to find magnetic field produced by this wire at this point P, take small element on this wire of length TL at a distance equal to L. At a distance equal to L from this point O as shown in figure. And the distance of the small element from this point P take equal to R. This is position vector of point P. This is length vector. The angle between length vector and position vector of point P, we always take theta. This becomes pi minus theta. This angle you will get how much? Pi minus theta. Now, first write down by Biot-Savart law. The magnetic field produced by this small current element at this point P, denoted by dB. It is how much? Mu 0 upon 4 pi ideal sine theta upon r square. Mu 0 upon 4 pi ideal sine theta upon r square. This is the magnetic field produced by that small element at point P. The direction of magnetic field at point P will come inward. Inward means perpendicular to the plane of figure and inward. This will be the direction of P, dB, produced by the small element at point P. To get total magnetic field produced by this whole wire, which is infinitely long, you have to take here integration of this. If we take integration of this by applying limits 0 to infinity, then we will get here magnetic field produced by only half part of that wire. To get total magnetic field produced by this wire at point P, we have to solve this integration. P is equal to integration 0 to infinity 2 dB. Why we have taken here 2 dB? Twice of this dB. 1 dB is the magnetic field produced by this small element that we have taken from upper side. Similarly, there is lower side also. If we consider another small element at same distance, if we consider another small element at same distance from low side, the magnetic field produced by this element also comes equal to same. Therefore, the magnetic field produced by the current element which are at same distance from point O, it will come 2 dB. And now, to get total magnetic field, integrate this 2 dB by applying limit 0 to infinity. Writing the value of dB and solving this integration, you will get here 0 to infinity. Mu 0 upon 4 pi ideal sine theta upon r square. Sine theta and sine pi minus theta, they are same. First I am taking here mu 0 upon 4 pi I upon r square out of integration. In integration, you get 0 to infinity dl sine of pi minus theta upon r square. Sine pi minus theta and sine theta, they are same. Trigonometric relation. You can replace sine theta by sine of pi minus theta. Now from this figure, sine pi minus theta, it comes r upon r. Therefore, I am writing here dl r upon r. This is r upon r. Take this r upon r also out of integration. In integration, you will get dl only here. In integration, you will get dl only here. This r, small r, is not constant. It will not come here out of integration. Small r is not constant. It will not come here out of integration, because it is the distance of point P from that element. It is variable. It will not come out of integration. Here you get mu 0 r upon 4 pi integration 0 to infinity dl r upon r square. You can take this r, which is fixed, out of integration. In integration, you will get here dl upon r cube. In integration, you will get dl upon r cube. Writing this r from figure. Writing this r from figure. How much? In root r square plus l square or l square plus r square by Pythagoras. Writing this r from figure in root l square plus r square. This is mu 0 r upon 4 pi, 0 to infinity, 0 to infinity dl upon L square plus R square raised to 3 by 2. If we solve this integration by using substitution L equal to R tan theta, the value of this integration, it comes equal to how much? It comes equal to 1 upon R square. 1 upon R square. There is a 2 here. This comes mu 0 upon 2 pi. Write this mu 0 upon 2 pi. There is a 2 pi. Cancel 1 r. You get here expression for this magnetic field, mu 0 into r upon twice pi r. Mu 0 into r upon twice pi r. This is the magnetic field produced by this infinitely long current carrying straight wire at a point which is at a distance equal to capital R from this wire. This is how to find magnetic field produced by current carrying straight wire using Biot-Savart law. Now after this, we will find force. Force acting on two parallel wires. Force acting on two parallel wires per unit length. Per unit length. How to find this force? See, take 2 wires. These are the 2 wires, long wires, straight wires, through which current I1 and I2 is passing in same direction as shown in figure. The distance between these 2 wires is equal to D. Distance between these 2 wires is equal to D. We have taken 2 parallel wires, long, straight, separated by distance D, through which current I1 and I2 is passing as shown in figure. We observe that on both wires force acts. The nature of this force is attractive. The nature of this force is attractive. If current passes through the wire in opposite direction, then the nature of force acting on these 2 wires comes repulsive. When the nature of force comes repulsive? When the current passing through the wire is in opposite direction. Here we are finding this attractive force because we have taken current in same direction. So that length of each wire is equal to L. Length of each wire is equal to L. The magnetic field produced by this force wire D. Magnetic field produced by force wire at a distance D, denoted by B1. Using previous expression, we get this B1 mu 0 I upon 2 pi D. The direction of this B1 by right hand thumb rule, we get inward, perpendicular to the plane of figure and inward. This is B1. Magnetic field produced by first wire at a distance equal to D. This second wire is in this B1 field. This second wire is in this B1 field and current is passing through that wire. I2 current is passing through that wire. Therefore, on this current carrying wire, which is in magnetic field, a force will act. This force, denoted by F2, it is a force acting on second wire. Force acting on second wire denoted by F2. You will get this, how much? Current into wire, current passing through the wire into length of that wire into magnetic field in which that wire is present. Write down the value of B1 here. We get this I2 into L into mu 0 I1 upon 2 pi D. Here there is the I1. It is a magnetic field produced by this first wire through which current I1 is passing. You will get this F2 mu 0 I1 I2 into L upon 2 pi D. See the direction of this F2 by right hand rule. What is the direction of F2 by right hand rule? Take 3 fingers of this right hand, thumb, forefinger, middle finger. I am taking this forefinger in the direction of current and this middle finger in the direction of magnetic field. The force will come in this direction, that is towards this side. This is the direction of force acting on this second wire towards first wire by right hand rule. This is the force acting on this second wire. Now similarly, write down the magnetic field produced by the second wire at a distance D, denoted by B2. It will come mu 0 I2 upon 2 pi D. This is the magnetic field produced by the second wire at a distance D. By right hand thumb rule, the direction of this magnetic field is outward, that is towards you, perpendicular to the plane of figure and outward. This is the direction of B2 here, which is outward towards you. B2 we have written mu 0 I2 upon 2 pi D. In this B2 field, in this magnetic field produced by second wire, first wire is present through which current I1 is passing. Therefore, on this first wire also force acts. I am writing here force acting on first wire. Force acting on first wire. It is F1 equal to current passing through first wire into its length into magnetic field in which that wire is present. Here, take B2. Using that value of B2, we get this F1 I1 into L into mu 0 I2 upon 2 pi. This is mu 0 I1 I2 into L upon 2 pi. This is equation 1. This is equation 2. See that both the forces are same in magnitude. Both the forces are same in magnitude, and if we find the direction of this F1 by right hand rule, it comes towards this second wire. Only directions are here opposite. The force acting on first wire will come in this direction, that is towards right side. Force acting on this second wire will come towards left side. This is the force acting on two parallel wires. They are attractive in nature. This force is attractive in nature. The force acting per unit length on this wire will come mu 0 I1 I2 upon 2 pi d. This is the force acting per unit length on these two parallel wires, which is attractive in nature. If the current passes in opposite direction, then the force of nature comes repulsive. The force acting on the second wire will come in this direction. Force acting on this first wire will come in that direction. Means these two wires show repulsion from each other. This is the force acting on two parallel wires. Now after this, we will find magnetic field by circular arc of wire. Magnetic field due to circular arc of wire, which is also one application of Biot-Savart law. Magnetic field due to circular arc of a wire. Magnetic field due to circular arc of a wire. Take one circular arc of a wire of length L, which subtends an angle theta with the center. Suppose point O is the center. This is circular arc. Current passing through this wire is I. Length is L. Not necessary to show this length here. This is center. Magnetic field due to circular arc of a wire at its center. We will find magnetic field at the center. How to find this? This is circular arc of a wire subtending an angle theta with the center. First, take small element of the circular arc of length dl and right here the magnetic field produced by the small element at center by Biot-Savart law. You will get here by Biot-Savart law. The magnetic field produced by the small element at center dB, it is mu 0 upon 4 pi r dl sin theta upon r square. Theta is angle between length vector of that element and position vector of the point, which is here 90 degree. Therefore, I am writing here 90 degree. Angle between this length vector and this position vector. Length vector comes along the tangent. Tangent is always perpendicular to radius. Sin 90 is 1. Therefore, we get this mu 0 upon 4 pi RDL upon R square. This DL, which is length of this small element, you can write in terms of this angle d theta. Consider angle subtended by the small element at the center d theta. We can write in terms of this angle d theta r into d theta upon r square. Radius is here capital R. Radius is here capital R. Radius is here capital R. Here also capital R. Radius into angle subtended by an arc with the center gives us length of an arc. Cancel one r from this. We get mu 0 upon 4 pi I upon r d theta. This is d. To get total magnetic field produced by that circular arc at the center, take integration of this dp by applying limit 0 to theta. Angle subtended by the circular arc with the center is theta. Therefore, solve this integration. 0 to theta. dB is mu 0 I upon 4 pi r into d theta. Taking mu 0 I upon 4 pi r out of integration. In integration you get 0 to theta d theta. Integration of d theta comes equal to theta. Upper limit minus lower limit gives the same theta. Therefore, this field, it comes mu 0 I theta upon 4 pi r. How much this field comes? Mu 0 I into theta upon 4 pi r. This is the magnetic field produced by the circular arc at its center. From this result, we can find the magnetic field produced by a circular loop at its center. Just want to replace theta by 2 pi. You can write here B due to circular loop. How much? Mu 0 I into 2 pi upon 4 pi r. Means this comes equal to mu 0 r upon twice r. This is the magnetic field produced by circular loop at its center, which we have obtained from this relation just by replacing theta by 2 pi. This is the magnetic field produced by circular arc at its center. Next part I will explain in next video.